The first speaker is Witten from the Institute for Advanced Study. During the next 25 minutes, he will be revisiting three-dimensional gravity. Ed?
Thank you. Thank you, and thanks to the organizers for inviting us here to Madrid and providing such nice facilities for this meeting. So, we'll be talking about three-dimensional pure quantum gravity with the Einstein-Hilbert action, including a cosmological constant that we parameterize in terms of a parameter L of dimensions of length. It's been studied from many points of view, but its status is unclear, and we're going to be trying to rethink it today. Now, the main reason I'm interested in doing so is the BTZ black hole. With negative cosmological constant, there are black holes in 2 + 1 dimensions. A little surprising because 2 + 1 dimensional gravity is supposedly trivial. That is, it has no propagating modes. But because the theory is trivial, you might at least hope to be able to solve it, and therefore you might get a solvable model with black holes. At least above, well, in 4 dimensions, you couldn't hope to get an equally precise model with black holes. Now, the first observation about the theory is that by power counting, it looks unrenormalizable, like gravity in 3 + 1 dimensions, because G has dimensions of length. But that's actually wrong. The theory is actually finite in perturbation theory, modulo a field redefinition and a renormalization of the cosmological constant. That's so for the same reason that the theory is trivial. You can't both claim that it's trivial and that it's unrenormalizable. There's a conflict. In 3 dimensions, the Riemann tensor can be expressed in terms of the Ricci tensor, which, using Einstein's equations, is a multiple of the metric. So, or in shell, every conceivable counterterm is equivalent to the volume of space-time, that is, a renormalization of the cosmological constant. So therefore, the fact that it's trivial really means it's renormalizable, despite the power counting. And that's true no matter how you set up perturbation theory. But actually, there's a natural formulation in which perturbation theory is finite without any renormalization or field redefinition. That comes from the fact that classically it can be reformulated in terms of a gauge theory. You start with the fact that the spin connection, omega, is an SO2 gauge field, and you combine omega with the Vierbein, which I'll call E, to make a gauge field of what I'll call SO2, or that's assuming the cosmological constant is negative. You just make a 4 × 4 matrix with omega as a 3 × 3 block. The 4th column and row are the Vierbein. And then you find out that as long as the Vierbein is invertible, the usual symmetries of general relativity, that is local Lorentz transformations and diffeomorphisms, are equivalent to gauge transformations of A. So the usual symmetries, that is local Lorentz transformations and gauge diffeomorphisms, are the same as gauge transformations of A. Now this is actually true in any dimension, but there's something that's unique to 3 dimensions. What's unique to 3 dimensions is that you can actually write the Einstein-Hilbert action in a gauge-invariant form as a Chern-Simons theory. That doesn't have an analog in 4 dimensions, and it's the reason that this naive relation of gravity to gauge theory is more useful in 3 dimensions. Now, if you approach perturbation theory via gauge theory, then it actually has better properties. Now it's actually renormalizable by power counting, and it's even finite because the Chern-Simons coefficient isn't subject to infinite renormalization. So to the extent that gravity is equivalent to gauge theory, you have not just a renormalizable theory, but a finite perturbation expansion. Well, is gravity equivalent to gauge theory? It's pretty clear that that's correct in perturbation theory. It's valid classically, well, it's valid whenever the Vierbein is invertible. That was the main step that we needed to justify the relationship. It's classically, by definition, we require that the Vierbein is invertible. And if it's invertible, then under perturbations it remains invertible. So in perturbation theory, this is okay. But non-perturbatively, the situation is unclear. Non-perturbatively, the situation was unclear because in gauge theory we allow the Feyerabend to be invertible, and in classical general relativity we don't want that. So my own view when I worked on this before is that the gauge theory description was the correct one non-perturbatively, and one had to allow a degenerate Feyerabend to make sense of the quantum theory. I don't know if that's the right interpretation. It's actually been criticized. For example, Seiberg pointed out that when we know how to make sense of quantum gravity in low dimensions, we take seriously the invertibility of the Feyerabend. So there are a lot of issues you can worry about, but regardless of the traditional questions, there's actually a worse problem with the gauge theory approach. The worst problem with the gauge theory approach is the black hole. Not so long after the gauge theory approach was suggested, it was pointed out that even though it's trivial, three-dimensional gravity actually has black holes if the cosmological constant is negative. And later it became clear that you should take these black holes seriously. Well, the BTZ black hole in 3 dimensions, so it's a 2-dimensional space, so a black hole, it's an extended object, its boundary is a circle. So it has a horizon length, which is the analog of the horizon area, and it's got a Bekenstein-Hawking entropy that's proportional to the circumference of the horizon. So it's supposed to have a huge degeneracy of quantum states. And although attempts have been made, I don't believe it's going to be possible to get this huge quantum degeneracy from the gauge theory approach. So I think that means that there's something missing in the gauge theory approach. And therefore, we're not really going to follow it. Well, we're sometimes going to follow it and sometimes not. We don't know when to follow it. Now, we're going to try to suggest what might happen, but in order to do that, let's discuss what we want to aim for. Well, first of all, we're only going to consider the case of negative cosmological constant. Well, first of all, there are some arguments that quantum gravity with positive cosmological constant doesn't exist non-perturbatively. That a world with a positive cosmological constant might be unstable. One reason for this is that it looks hard with positive lambda to define precise observables. That's natural if such a world is unstable. If a world with positive cosmological constant is unstable, then it would have to be treated as an approximation to some bigger system. And you would not expect to solve it by itself. You could embed it in a bigger system, but then that bigger system might be extremely complicated. For example, with positive lambda, you could embed three-dimensional gravity in string theory, but then it's not trivial anymore, and you wouldn't hope to get an exact solution. So, whether or not it's the case that a world of positive lambda doesn't exist by itself, since there isn't a sufficiently clear-cut proposal concerning precise observables one could try to calculate, we don't have a good enough idea of what it would mean to solve it, and therefore we're not going to try to. Now, with zero cosmological constant, above 3 dimensions, there's a clear-cut observable, which is the S matrix, for scattering of asymptotic states. In 3 dimensions, we actually don't have that observable for a variety of reasons. There are no gravitons, and if we do pure gravity, there are no local propagating fields. And there also are no black holes, because the BTZ black hole is only for negative cosmological constant. So we don't have an S matrix, and again, we don't know what we'd be trying to do in trying to solve it, so that we won't try to solve it. If anyone wants to say what it would mean to solve it, we can try, but in the meantime, we won't. Now, with negative cosmological constant, there's an analog of the S matrix, namely the correlation functions of the dual conformal field theory. And this captures the asymptotic information that's analogous to the S matrix for lambda equals 0. It's actually much richer than the S matrix. So not only for negative lambda is there an analog of the S matrix, but it's much richer. And not only it makes sense in 3 dimensions, but in fact one of the early precursors of the ADS-CFT correspondence was precisely in 3 dimensions in the work of Brown and Hanot. Brown and Hinault considered three-dimensional gravity maybe with matter fields. That's what these dots represent. For what I'm about to say, it's not important to be pure gravity. And they showed that the Hilbert space of this theory with negative cosmological constant has an action of left and right moving pair of Virasoro algebras with a certain central charge. In our modern understanding, this Virasoro action is part of a much richer structure, the dual conformal field theory. So what it means to solve the theory for negative lambda is to find the dual conformal field theory, and we focus on negative lambda because that's the only case where we have a clear picture of what it would mean to solve the theory. Now, if you approach it this way, then there's something which is obvious, even though it's rather surprising classically. We're going to go back to pure gravity. And now there's a constant in the Lagrangian, L. It's basically the cosmological constant in Planck units. Classically, it looks like a free parameter. But the formula for the central charge shows that that's wrong. The dimensionless ratio L over G can't be a free parameter, because it's the central charge of a conformal field theory. And according to the c-theorem, whenever you have a two-dimensional conformal field theory that depends on a variable parameter, the central charge is constant. For example, the central charge of a Clavier is independent of the moduli. That's an example of the theorem. So the cosmological constant cannot depend on a variable parameter such as L over G. It must be that three-dimensional quantum gravity makes sense at most only for certain values of L over G. Now, there is, we should say, an important technical assumption about the c-theorem. The c-theorem applies to conformal field theories that have a normalizable and SL2 invariant state. I'd say that that assumption is valid for three-dimensional gravity with the anti-de Sitter space as the classical approximation to the quantum state. The SL2 times SL2 symmetry of the anti-de Sitter space is an approximation classically to the SL2 times SL2 symmetry of the corresponding quantum state. And anti-de Sitter the fact that three-dimensional gravity is said to be trivial tells you that anti-de Sitter space is stable. If it was unstable, it would at least have to be non-trivial. Now, I should remark that the statement that L over G can't be continuously varied didn't depend on having pure gravity. It's also true in other ADS models with matter. And another example is that in the familiar ADS models, the string theory models whose duals we know, L over G is expressed in terms of integer-valued fluxes, and that gives a direct explanation of why it cannot be varied. But the c-theorem says that more generally, L over G can never be varied. So we're only going to solve the theory for negative cosmological constant, and even then only for certain values of L over G. But what are the right values? Well, we don't have any honest way to find the right values. There's a simple picture that gives us a plausible heuristic way to find some preferred values, and it turns out that it gives interesting values. I don't claim anything for this. It was all I could think of to find distinguished values, and to some extent, I knew what I wanted to get, so I used some sleight of hand as necessary, as you'll see if you read the paper carefully. We're just going to take at face value the gauge theory description of pure three-dimensional gravity, even though I told you we couldn't trust it for all purposes. So, first of all, in addition to L over G, there's really a second dimensionless parameter, since you can add to the action a multiple of the Chern-Simons invariant of the spin connection. And here, this is just a conventional Chern-Simons interaction, so K is quantized for topological reasons. And this was pointed out by, I think, Deser and Jakiv roughly 25 years ago. The theory depends on two parameters, L over G and K. We understand why the second is quantized, and we'd like to know why the first is quantized. And we're going to get them both the same way by interpreting them both as Chern-Simons invariants. We're just going to take at face value the gauge theory description of three-dimensional gravity, And that'll give us, if we take it literally, an explanation of why the parameters only take special values. So, well, we use the fact that the gauge group is essentially SO21 times SO21. And the two SO21 gauge fields are the spin connection plus or minus the Fierbein. Once again, this only makes sense in 3 dimensions. Because only in 3 dimensions the Fierbein and the spin connection have the same quantum numbers, so you can add and subtract them. So then the gravitational action with that Chern-Simons term added takes this form. It's a sum of 2 Chern-Simons invariants for A plus and A minus, and they're both quantized. If you take the gauge theory description literally, then KL and KR are both quantized to integer values for topological reasons. And moreover, if we then also use the results of Brown and Haenel and the gauge theory, the gravity Chern-Simons relation, then we find that the central charges are 24 times integers. So a 2-dimensional conformal field theory has a left and right central charge, and they are 24 times these 2 integers, k left and k right. Now that came by assuming the gauge group was SO21 times SO21. We could have replaced SO21 times SO21 with some kind of covering group, and then more values would have been allowed. But I don't want to. I like this answer, so I prefer to assume that the gauge group is precisely SO21 times SO21. That's a good answer, because in 2-dimensional conformal field theory, holomorphic factorization is possible precisely for these values of the central charge. So the values of the central charge that we get, at least if we assume this gauge group, are hints of holomorphic factorization. There's a more elementary hint, which is simply that the action is the sum of an action for k left and an action for k right. This one leads to the left Virasoro, and this one leads to the right Virasoro when you make the Brown-Haenel argument. So the fact that the action is a sum of 2 actions corresponds to the theory being a product of 2 theories, naively. And similarly, for whatever it's worth, the black hole entropy of the BTZ black hole is the sum of a function that could be interpreted as a left entropy and a function that could be interpreted as a right entropy. So there are a variety of clues, if you're willing to be an optimist, suggesting holomorphic factorization, and one of them, which admittedly involved a little sleight of hand with the choice of the gauge group, is the values of the central charge. So in continuing, we're going to assume holomorphic factorization, and we'll just try to describe the holomorphic part of the theory, which will be a holomorphic CFT with central charge 24k for some integer k. Now, one simple fact is that the ground state of such a theory is minus c over 24, which is minus k, and that's an integer because c is 24k. The fact that this is an integer is part of holomorphic factorization, why it's only possible at these values of c. Apart from the ground state, what else is there? Well, naively, nothing, since 2 plus 1 dimensional gravity is said to be trivial. But that isn't right. At least there are the boundary excitations that were discovered by Brown and Haenel. And if that was all, then this would be the partition function in genus 1. I've just written down q to the minus k, where minus k is the energy of the ground state, and then this is the function that counts the Virasoro descendants of the ground state. So this function counts the excitations that we can make by acting repeatedly with the stress tensor and its derivatives on the vacuum. But it can't be the full answer because it's not modular invariant. There have got to be some additional primaries apart from the identity. So the partition function might agree with this one for small values of the energy, but there's got to be some correction. Now we'd like it to agree with this one for small values of the energy, because naively the theory is trivial, pure gravity, and we've retreated from claiming it was completely trivial to allow the boundary excitations of Brown and Haenel, but that's all there appears to be in classical pure gravity. So at least this should be a good approximation to the answer, which will take to mean that L is pretty big. We're going to interpret the fact that the theory is classically trivial to mean that we should make L as big as possible. Turns out that the largest that L can be is k plus 1, and if this is the right value, then the partition function is uniquely determined. So my proposal is that this gives the partition function of the dual conformal field theory, including the black holes. So I want to explain this statement, that if L is k plus 1, then the partition function is uniquely determined. So the partition function is a function of the moduli of a Riemann surface of genus 1. And such Riemann surfaces are classified by something called the J-invariant, which has this kind of expansion in powers of Q. There's a Q inverse and some more stuff, and a lot of very big numbers, even bigger if I went farther. It's convenient to subtract the constant and use capital J, which also can be used to parameterize Riemann surfaces. And the fact that capital J parameterizes Riemann surfaces means that modular invariance is equivalent to the partition function being a function of capital J. But the only pole of the partition function is supposed to be at q equals 0. Because the partition function is trace of q to the h, it has a pole at q equals 0 because the ground state energy is negative, but it doesn't have any other poles because the trace converges. If you like the Cardi formula or something, gives a bound on the asymptotic growth of the states that shows that the trace converges whenever q is less than 1 in absolute value. So the only singularity is at q equals 0. Q equals 0 is j equals infinity, since j is infinity when q is 0. So the partition function is a function of j that's infinity only when j is infinity. In other words, it's a polynomial in j. And since, on the other hand, since z is supposed to have a pole of order k, because the ground state energy is minus k, that means that z is a polynomial in j of order k. So z looks something like this, with some coefficients a sub r. It's a polynomial in the j function of degree k, so it's determined by k plus 1 coefficients. And now we want to make such a function as this agree with this as well as we can. Well, the best we can do is to agree with the first k plus 1 coefficients. So we'll agree with the first k plus 1 coefficients starting at minus k and going up to 0. And that means that in order q to the 1, we don't have any control over what's going to happen. It's uniquely determined. So our partition function, making the first k plus 1 coefficients agree with this, determines all the coefficients, the a's. Making the first k plus 1 coefficients in q agree with this, determines the a's, and therefore determines z. So for every k, I've told you what z is supposed to be. We've got no control over the term of order q to the 1. This is above the ground state by k plus 1 units, so it means there will be primary fields of dimension k plus 1. And we interpret them as primaries related to black holes, since the theory is trivial except for the Virasoro algebra, which we already took into account, and the black holes. In fact, something nice happens. The minimum classical black hole mass in these units is k, but the black hole entropy is 0 at k equals 0. So, well, I'm now squeezing more out of the classical argument than is really to be had, but naively speaking, black holes of positive entropy exist only if the mass is greater than k, which agrees with our quantum proposal that the lowest dimension of a primary other than the identity is k plus 1. Moreover, the partition function that I described agrees with the Bekenstein-Hawking entropy. Black holes weren't put in describing it. We just decided that we'd implement the idea of having nothing for as long as we could. But that gave a uniquely determined partition function that agrees with the black hole entropy. That might sound like a miracle, but if you're familiar with previous results in three-dimensional ADS-CFT, such as the fairy tale story in this paper, then it won't be so surprising. Now I want to give an example, and for the example we'll take the largest possible value of the cosmological constant, or in other words, we'll take k to be 1. In that case, the partition function is J itself, and therefore it's equal to Q inverse plus 196,884Q, and so on. Now, one of these states is the stress tensor. So the number of black hole primaries of mass 2 is 196,883. And therefore, the black hole entropy is the logarithm of 196,883, which is 12 point something. And it agrees reasonably well with the Bekenstein-Hawking entropy, which would be 12.57, or 4 pi. This was the worst case since we took k to be 1. The Bekenstein-Hawking formula is good when k is large and m over k is held fixed as k becomes large. So by taking k to be 1, we took the worst case, and the Bekenstein-Hawking formula was still correct within a few percent. So the other cases are only better. But let's go back to k equals 1. The number 196,883 of black hole primaries is a very special number. Back in the 70s, the last of these sporadic or exceptional finite simple groups was constructed, the Fisher-Grease monster or friendly giant. The lowest dimensional representation of an irreducible representation is 196,883. And John Mackay noticed that this is very close to that number that we just encountered as the coefficient of the, well, first really interesting term in the J function. Frenkel, Lepowsky, and Meurman explained this by constructing a holomorphic conformal field theory with partition function our friend capital J of Q. Well, they also conjectured that their theory is the unique one with this partition function. Well, if their conjecture is correct, then their theory must be dual to three-dimensional gravity at that value of the cosmological constant, according to our interpretation. And at this value of k, we can make the case stronger because, well, it's actually been argued by Schelikens, I think possibly not completely proved mathematically, that at c equals 24, there are precisely 71 holomorphic CFTs. 70 of them have dimension 1 primaries, which in ADS CFT would correspond not to pure gravity, but to gravity coupled to some gauge fields. So, okay, that's what those 70 theories are. So if we want to do pure gravity, it must be the 71st theory, the monster theory. So we can interpret the monster group as the symmetry of three-dimensional black holes, at least at this value of k. What about higher values of k? The big question is whether extremal CFTs exist, and secondarily, do they have monster symmetry? There's a similar story for the supersymmetric case, though I don't have time for it. The natural values are 12k instead of 24k, and appropriate examples are known if k is 1 or 2. But where they were found and discussed, most importantly, by these authors. And I guess I'll stop here.
Thank you very much. Are there any questions?
So since you explained that the theory is basically trivial, can you form black holes from something else in a natural process and so on?
Well, the only thing you could form black holes from would be other black holes, because that's all there is.
So you have mergers?
And the closest analog of a black hole merger process is to take primary operators that individually would create fairly small black holes, act on the vacuum with the product of such primary fields, which can create a very big black hole. That's the closest analog of a four-dimensional process of creating a big black hole out of little things.
And one more question. Do you get any kind of indication about what resolves the singularity inside the black hole from this picture?
Not me. But the dream, of course, would be to describe the CFTs concretely for all k, and then to demonstrate that for large k, they have the semi-classics that was predicted by gravity. Even if you could implement that, it might not answer your question. But it would be a nice thing to do.
There is one more question over there, Andy. At the microphone here.
You presented your argument as somewhat sensitive and conjectural, but I'm wondering is there some way that it could be wrong? I mean, what's preventing you from saying you've both defined and solved the theory? Could there be some
Well, I can see a number of things that might be wrong. First of all, there's no money-back guarantee that a quantum theory corresponding to pure gravity exists in 3 dimensions.
Well,
Secondly,
you constructed something that satisfied all the...
Okay. No, sorry. At c equals 24.
I see. Yeah.
At c equals 24, it's probably okay. Let me point out the following. If it's limited to special values of k, then there isn't a cogent argument for claiming that it's pure gravity. What it would mean to solve pure gravity would be to solve the theory for an infinite set of values of k, and somehow be able to claim that pure gravity was the asymptotics. I think if it only exists at c equals 24, it's a matter for poets and philosophers to decide whether it's pure gravity.
I see.
When I said it wasn't clear that pure gravity exists, what I mean is that it's not clear it exists except for special values. Secondly, the argument for holomorphic factorization, certainly, to put it mildly, wasn't bulletproof. And I gave a naive interpretation of what it meant to say that there was nothing, as well as I proposed that there were no primaries up to dimension k plus 1, but that was just a guess. I would say every step was shaky.
And if I may have a second question, which is,
yes.
There's some work a few years ago, and I may be getting the authors wrong, but I think the ones I remember are Felstead and Huang, in which they start with the gauge theory approach, and they look at twisted sectors, and they count some stated, some twisted sectors. They have a long string, and they need to have twisted sectors up to k twists. And they reproduce in that way the black hole entropy, which, as you point out, is almost the same. Getting the black hole entropy right is almost the same as demanding modular invariance. I'm wondering if you looked at that and if you thought that could be related in any way.
I'm afraid I haven't looked at it seriously. I'm sure I should.
Okay, there is one more question over there. Yeah.
Thank you. So in this mass gap between the ground state and the sort of slightest black hole, I mean, people have speculated there might be, particle-like states, which are represented just by conical singularity in the geometry. Are you saying that these are just not states of the quantum theory?
Well, certainly in my proposal, they're not there. Now, is my proposal right? I don't really know. If you said that there are, I assumed that there was a gap as big as there could be up to k plus 1. If you wanted to postulate a gap up to k, or up to half k, or 0.9 k or something, it wouldn't really contradict anything I know. It seems a little bit arbitrary. I don't see any clear argument for assuming anything in that range. And it's nice that modular invariance and holomorphic factorization gives a unique answer if you assume there's nothing in that range. If you assume that there was a whole continuum of conical singularities of any deficit angle, I would say that that contradicts the idea that the theory is pure gravity, if that went down to low masses. You see, as long as you put whatever you're planning to add up at the Planck mass, then in principle I don't know about it. For a large k, there are 2 mass scales here. There's the Planck scale and the scale set by the cosmological constant. Saying that the theory is pure gravity means that at the big scale there's nothing. But I don't know what there is at the Planck scale. So I don't claim my proposal is any more than an ansatz. So if you or anyone else has another proposal where there's something else at the Planck scale, I can't contradict it.
Okay, there is one more question, Cyber over there.
Is it clear that you solve these equations for the AR, for the coefficients, and then you plug it back in and you find the partition function? Is it clear that the coefficients of the Q expansion are positive integers?
It turns out to be easy to prove that. I didn't mention it in the talk, but you can prove that they're positive integers. And that might give us a small amount of encouragement that we're on the right track.
Okay, there is one more question over there, up there. Okay. Wait, just a moment. Let's go here first. Okay.
Do you expect that eventually this can be embedded in string theory?
Well, it seems reasonably plausible that if the landscape really exists, This is a kind of extreme of landscape state. Landscape states correspond to conformal field theories with relatively big gaps. Here we're going all the way to have the biggest gap that's imaginable. So if this exists, it's the extreme end of a landscape CFT. I can't promise it. Maybe it can only be embedded in string theory for some K. The question is a little bit unclear, because we don't know in general what's the real world of ideas that represent string/M theory. Probably. The answer is probably yes, if we're really interested in what string theory was. But I think you meant more narrowly, if there was a compactification from 10 or 11 dimensions to this. That's a little bit harder, but this is in the spirit. Maybe only for some values of K you would hope to get this.
Okay, up there, there's one question.
What's the motivation for assuming that the boundary CFT is holomorphically factorized?
Okay, no argument is bulletproof. I thought, okay, we had to find some good values of C. And I decided I was going to use the gauge theory approach, even though I'd criticized it earlier in the talk. And the gauge theory approach, if we just interpret the gauge group as SO21 times SO21, gives us C being a multiple of 24, which happens to be the values at which holomorphic factorization is possible. A holomorphic factorization is a drastic simplification. So if those are the right values of C, we wouldn't want to look a gift horse in the mouth and not assume a holomorphic factorization.
Well, sure, but you could have taken SO22, which in that
well, I could have, but I might have been
C a
wrong.
multiple of 6.
You can do that. It might be right. I don't know the rules for sure. I decided, I have to admit, I don't want to deceive you. I knew the answer I wanted to get, but I tried to think of a way to get that answer. I wanted to be able to have something that you could possibly solve, and that more or less meant it had to be holomorphically factorized. So there had to be a reasonable reason that C had to be a multiple of 24, and SO21 times SO21 gauge theory was the best I could do. You'll have to decide for yourself whether you find it convincing either a priori or ex post facto. It's up to you.
Okay, there is one more question over there. Please, the microphone. Here. Yeah.
Three-dimensional gravity also needs other solutions like black holes that have non-trivial topology behind horizon or wormhole solutions. Do they fit in this proposal?
Well, I can't answer all those questions, but some of them are not clear in ADS-CFT in general. Some of them are. For example, the Schwarzschild solution with two asymptotic regions has been interpreted in terms of an entangled state. But not all such questions have been answered. But I don't think I have anything new to say based on this.
Any other question? There is one over there. Just microphone, please. Yeah.
So for low mass, you said that your entropy was off by a few percent from
yes.
that expected from Wittgenstein-Hawking. Now, can you show explicitly that for large masses, your formula goes, or your results go over to Wittgenstein-Hawking?
Yes, but you have to specify exactly what it means. Wittgenstein-Hawking is valid for large K and fixed M over K. And in that region, you can show it explicitly, and I did, but it's, there are other ways to show it, and it's a more general result. It's not, it's true, but I'm not sure how deep a test it is.
Okay, thanks.
Any other question? Okay, if not, let's thank our speaker again. Thank you.